Hello, this is Mark Struthers. Today we want to talk about some fundamental facts about MRI technology that you need to understand prior to actually studying the physics of MRI. What we call today magnetic resonance imaging was originally described as nuclear magnetic resonance imaging. Rather than intimidate everyone starting out with a lot of physics and numbers and equations, let's take a look at a few of the fundamental concepts that needed to be understood prior to conceptualizing those equations. An MRI technologist needs to understand anatomy and physiology, not only in the 2D perspective, but in cross-sectional anatomy as well. We need to know anatomy and physiology to record the data required to create MRI images for diagnosis. In addition to anatomy and physiology, the MRI technologist must also understand a very complex imaging system that includes magnets, gradient coils, radio frequency coils, and a system computer high-performance processing system. Once the MRI modality captures the data or signal, you need to have an in-depth knowledge for both the physician that is doing the interpretation and the technologist acquiring the data of analog to digital conversion in digital imaging. These are the important tools and concepts that you must understand to add to your extensive knowledge of medical imaging and patient care. For those that study MRI, they usually focus on the physics of MRI, but that is only a minor portion of the knowledge base that you will need to be successful. So let's start exploring MRI and the concepts associated with MRI. The signal generated for MRI images originates with the magnet, the gradient coils, and the radio frequency coils contained within the main unit. MRI works by passing an electric current to create a temporary magnetic field in your body. A transmitter receiver in the machine then sends and receives radio waves. The computer then uses these signals to make digital images of the scanned area of your body. We will review this process in more detail as we go through the presentation. The human body is full of random micromagnets. They cancel each other out as they are both positive and negative. If a strong external magnetic field is applied to the human body, it aligns the protons north to south. The aligned protons are all the same strength. So how do we figure out where we're looking in the body? How do we get a slice or a cut? We turn on and off the gradients to superimpose a second magnetic field from the gradients over the main static field. Let's take a look at the main static field and its strength. The knocking sound you often hear is the movement of the gradient coils being turned on and turned off. So what does that pattern or knocking means? It means we're developing and utilizing pulse sequences to disturb the main magnetic field. This is how we select the data to be utilized in creating the images, by pulsing RF signals into the static magnetic field. There are basically two types of RF signals. There is a spin echo and a gradient echo. How we pulse these determines what type of images that we will get. The two basic types of MRI images are T1 weighted and T2 weighted, often referred to as T1 and T2 imaging. The timing of the radio frequency pulses used to make the T1 image results in images that show more tissue. As to T2, those images dominate by showing more water or fluid. Here we see T1 and T2 weighted images of tissue and fluids as we go through the brain. The second method of getting images using radio frequency pulses is through the use of gradient echo pulsing. Utilizing turning on and turning off the gradients, we are selecting the data that they produce at the time that they're on. We can select how we turn these off and turn these on, and we select them by what they are representing, either the Z, Y, or X body plane. They are turned on and off during the period of free induction decay of the RF signal. Now we're going to move forward and we're going to look more in detail at the utilization of radio frequencies and magnetization. The power of the modality depends upon the main magnet field, or the Tesla. The more Tesla, the more power, the shorter the times needed to gather data. The protons spin at the frequency that corresponds to the magnetic field. The higher the field, the higher the spin frequency. When a hydrogen proton spins at 0.5 Tesla, it has a different strength or frequency compared to a proton spinning at 3.0 Tesla. As protons align with the magnetic field, they also precess or wobble, just like the Earth as it aligns with its magnetic field. They do not spin totally horizontal and vertically. They precess. This is known as spin resonance, whereas if we looked at just spinning vertically, that's what happens with current. As we move forward, you'll need to really understand spin resonance and spin current, which is understanding spin and spin. This is where most people get confused. Remember, while the protons are precessing around the electromagnetic field, or wobbling, the electrons of each proton is circling that proton in a true spin. That's why we talk about spin and spin. MRI locates and measures areas of naturally occurring substances from an image. The protons are in motion, switching from low field to high field of the magnet. This means that the protons are flipping from high energy to low energy, and the reverse, low energy to high energy, constantly. A snapshot in time would always show that there are more protons aligned at the low energy field than there are at the high energy field. So we would have more protons aligned to the north along the magnetic field than to the south. As the protons align with the magnetic field, they align in one of the two orientations, parallel and anti-parallel, or either north and south. Those aligned to the south are in an excited state. Those that are exactly in the middle have no charge at all, and those that are going to the north are in a lower state of excitement, so they have less energy. We use an RF signal pulse to add energy to the protons that are in the north or less excited phase to go ahead and get them more excited and push them down so they're in the south, in the very excited phase with the other protons already in the south. We then eliminate the RF signal. When those protons that we excited from the north to go to south have no signal to push them there, they realign to the north. During this realignment, they give off energy, or they have energy decay, until they have less energy and can be realigned with the north. We document this decay or energy loss in frequency as the photons realign to the north. They are losing energy as they realign, and this is called free induction decay, FID. The movement of protons to the south by adding energy and then aligning the protons back to the north is called a spin echo. As we map the energy release, we map it over time, and this is called T1 and T2. So we know exactly what energy is where at what specific time. T1 is tissue weighted and T2 is fluid weighted. So to recap, tissues with magnetic moments are tipped out of alignment by a radio frequency pulse. The protons in the tissue absorb energy from this radio frequency pulse. When the pulse is terminated, the tissues release that energy they had absorbed as free induction decay. This energy released by each tissue is unique, as each tissue has a unique proton structure. The released energy is used to create maps of the MR energies, and these maps of the MR energies are producing data that can be put together as an image, either a T1 image or a T2 image. The timing of the RF signals and their collection of the decay of the signals is how we create different types of images in MRI, and this is called a pulse sequence. There are many, many types of pulse sequences. This is how we use techniques to get different types of tissue densities for diagnosis. We've looked at the acquisition using gradient and spin echo, but what are the acquisition parameters that are set by the person creating the images? What are the acquisition parameters? Just as techniques are set for ionizing radiation imaging, we also have parameters that need to be set for techniques in magnetic resonance imaging, and these vary dependent upon the facility, the strength of the magnet you have, and the type of images you need to collect. Before we get too deep in the weeds, let's get back to basics. Here we can see how we can select the slice or the area of interest. For this one body plane, the combination of the main magnetic strength and the gradient field strength applied gives us different energies or areas that we can record. And this is how we make a slice or select the area of interest to be imaged. Notice we've already selected a slice at 1.3 Tesla, another slice at 1.5 Tesla, and our final slice will be at 1.7 Tesla. Gradient energy is applied to the static whole body energy from the magnet that is magnetizing the body to one level. By superimposing these two different strengths, we're able to locate different areas in the axial, sagittal, and coronal level. The RF energy is then recorded on a matrix to create images. A magnetic gradient is superimposed over the existing magnetic field to allow us to locate and map points or areas in the body. 3 separate gradients are applied, one for each plane of the body. To create differential points along the body, we turn the coils for the gradients on one side at a time, north, then south, and then north. And this is why you have that. That's the gradient actually torquing around the magnet. But while we're torquing, we're actually creating a slope in the magnetic field that is going to be superimposed over the existing magnetic field so that we can map points on the patient's body. In MRI, an image matrix is created which is comprised of pixels that represent the data collection from all 3 gradients at one specific point or pixel upon that matrix. An MRI image display is a matrix of pixels that are comprised of the data that was collected during the examination. Each specific pixel contains the data from the energy collected in the axial, sagittal, and coronal plane. So this gives us a 3D map of the patient's body, where we have choices of what we're going to do with the data that we have collected. We have 3 choices. The first choice, of course, is at isocenter, and we're going to choose that as the image slice. So we're going to select either axial, sagittal, or coronal, or anything in between, as the slice point at isocenter. That leaves 2 more pieces of information on each pixel to choose from. The next choice is that pixel location on that slice has a density or an intensity of what shade or brightness. It's like working with a color by number. Each pixel would be a number, and whatever the intensity is, the brightness, shade of gray or color, is mapped to that pixel. So we have the pixels, and we have their intensity, and we also have their brightness. What do we need next? Where are they? So the third point would be, where is that pixel in that matrix? When we put them all together like a puzzle, we have our image. So let's end this, and we'll end with a recap of what we have done, or the concepts that we presented. The MRI has the ability to image in different planes. These planes are defined by using the 3-dimensional Cartesian coordinate system that has axial, sagittal, and coronal, or X, Y, and Z planes. The X, Y, and Z axis constitute the 3 sets of magnetic field gradients as well. When switched on and off, protons at different points in the body experience their own specific combination of gradients and thus emit a unique signal. We capture those signals, and from those signals we create data or a display image.